Yeah. We'll start, sir. Good morning, one and all. Gathered through online from various places in India for faculty development program on recent trends in electrical engineering from 9th August to 13th August. Organized by Department of Electrical and Electronics Engineering, Aras Engineering College, Kumbakonam. Today is day 2 as well as session 2. Today's topic is soft computing techniques in high gain DC to DC converter, handled by Professor Dr. T.D. Sudhakar sir, Department of EEE, Saint Joseph College of Engineering, Chennai. First of all, I would like to I request our assistant professor Mr. A. Balasubramanian sir introduce our chief guest. Kindly, sir.
Thank you, sir. It is my privilege to give an introduction about our resource person for the FTP today's session, Dr. Sudhakar. Dr. T.D. Sudhakar was born on 14th June 1980 in Chennai, Tamil Nadu. He received a BE degree in Electrical and Electronics Engineering from Sri Sairam College of Engineering, Madras University in the year of 2001. He qualified in GATE 2002 with a score of 91.34 percentile. He did his master's in ME Power System Engineering from Tyagaraja College of Engineering, Madurai, Anna University in the year 2004. He has got his first PhD degree in the area of power system from Anna University. He is employed with the St. Joseph College of Engineering, Chennai as a professor and having more than 15 years of experience. He is currently pursuing his second PhD degree in power electronics in the Department of Electrical and Electronics Engineering of B.S. Abdul Rahman Crescent Institute of Science and Technology. His area of interest includes power system reconfiguration, grid-connected system, power quality, and DC to DC converters. He has published 42 papers in the journals and presented 45 papers in the international and national conferences. He is an editorial member in a journal and reviewer in
this opportunity in presenting a session on recent trends in electrical engineering. So it's a very broad area. So I am just confined to soft computing techniques in power converters using MATLAB. So my objective is to give a brief intro about a field, a part of power electronics, that is power converters. So the soft computing techniques is used here. So first, a brief outline of my presentation of what is soft computing techniques we'll be seeing. Later, we'll be seeing what is dealing above solar energy, MPPT algorithms, and a small introduction about DC-DC converter, and then closed loop control techniques and some simulations regarding the DC-DC buck converter and a type of soft computing, that is fuzzy system, and how all these things are used in our high gain DC-DC converter. A sample converter, self-flipped converter is taken and the analysis of it is shown here. So first of all, what is soft computing? So soft computing was first developed in the year 1981 by Lotfi A. Zaid. So the soft computing means simulation. So the soft computing application, which is main objective is to simplify and obtain accurate results, simplify the workflows of human beings. So some of the examples are fuzzy logic, neural computing, evolutionary algorithms, genetic algorithms, etc. So what is the main meaning of soft computing? So we human beings want alternative sources. So we require approach which can think as we are thinking. So we want a replacement or simplify our work. So for that purpose, a soft computing is emerged, which uses our human brain to reduce our task. So a soft computing is a simulation process which utilizes the human being's understanding, reasoning, and perception of building new tools. The soft computing can be put in other words like intelligent control, artificial intelligence, etc. So some examples of known things is neural network, fuzzy logic, genetic algorithm, expert system, ANN, swarm intelligence, and colony optimization, taboo search. So these are some of the core, but the development of random search technique was taking place like this. In 1981, as I said, it started, but the first algorithm was introduced in the year 1983, which was a simulated annealing. Okay, in short, we call it as SA. So this principle based here was thermodynamics. Earlier, the thermodynamics was the dominant one that time. So based on that thermodynamics, various concepts of thermodynamics are used, and based on which this simulated annealing was developed. And next one, in the year 1989, the algorithm which we know everyone, so genetic algorithm, which is survival for the fittest. So based on that genetic algorithm, the same concept, evolutionary programming. In genetic algorithm, we use the genes concept. So in our, which is based on our DNA, so that we use zeros and ones. Whereas in evolutionary programming, we use the numbers from 0 to 9. But the concept of genetic algorithm and EP are same. In 1995, PSO algorithm was introduced. PSO means particle swarm optimization, so which impacts the way in which birds fly. So how the birds arrange themselves in flying from one region to another region. So next one is ant colony optimization. So this ant colony, we know that always the ant moves from destination to source, that is from its place to in search of food. Always it finds it a shortest path. This ants segregates the sweat, based on their sweat follows. So
Hello?
whatever distraction comes in.
हाँ जी साहब सिंह जी बात कर रहे हैं।
Hello?
हाँ जी साहब सिंह जी, हम पानीपत से बात कर रहे हैं, सनातन धर्म एजुकेशन सोसाइटी से। आपका बच्चा है
Right?
ना
So the
सुशीला,
ant colony.
इसका ने टेस्ट किया था हमने इसके स्कूल में, गवर्नमेंट सीनियर सेकेंडरी स्कूल में। तो इसमें सर इस बच्चे की स्कॉलरशिप आई हुई है 2 कोर्स के लिए, है बीबीए और बीसी।
Hello?
अगर आप
Sir, please, sir, you can carry on. Someone will disturb you.
Okay. Thank you. So the ant colony is one which behaves. So whatever obstacle in the path of ant is created, yeah, additional route it will find out, which is the recent shortest path. So like that, lot of algorithms has been introduced. So we can see harmony search, electromagnetism, shuffled frog, bees colony, cat swarm optimization, how the cat behaves, firefly algorithm, gravitation. So like this number of algorithms, so day by day, it's the search up to 2014 is there. I will show you. So these are some of the bio-inspired algorithms, like genetic algorithm. So these are all some of the algorithms recently which is taking place. So search of virus based on that algorithm. So based on our kidney functions, kidney inspired algorithm. So these are all many algorithms are there which can be used in our soft computing techniques. So to simplify the work of the human beings. So yeah, main aim of this soft computing is to develop intelligent machines which helps the human beings to solve the complicated problems available for him in the real world. These soft computings are applied where mainly the mathematical models are difficult to formulate. For example, we apply soft computing to electrical power systems because where the network size is very, very big. So simple, we require some simulators to analyze it. For Y bus formation, if you are doing 3 by 3, you can do manually. 4 by 4, it is difficult to do manually. Whereas 6 by 6 or 10 by 10, so as the size increases, the complexity is increasing, and at one point of time, it is comes to a conclusion that human beings is very difficult to do this analysis. So for solving those type of problems, the soft computing is required. Okay, so where we can, it is very difficult. So in that case, we can do some approximation, and uncertainty is certain part of uncertainty is also allowed here. So we had two terms here. What is soft computing? We have seen, we have done hard computing. So soft computing, all we know is it's simulator based on this, whereas hard computing is, it is real time. So where in hard computing we cannot accept approximate answers, we want precise answers. So implementing all in soft computing is not possible in hard computing. So till now, the soft computing which is much successful in hard computing is fuzzy logic. So the fuzzy logic is, and to certain extent, neural networks. So the fuzzy logic is where we use lot of many applications. So for example, if you see fuzzy logic examples are many. For example, our TV, AC, or microwave ovens, washing machines. So these are all some of the hardware implementation of our fuzzy logic. So fuzzy logic is used in place where we have if and then rules. So this is a small thing of our soft computing. So little bit deeper into my topic, today's topic. So how this soft computing is used in our converter side. So this is a basic block diagram which I am going to consider now. So solar energy is used, that is given to a DC-DC converter. Why I am giving it to a DC-DC converter? Because solar energy is DC and that is given to an inverter. This inverter converts DC to AC, that is fed to a transformer, and then it is used in either grid or load. So in our recent trends in electrical engineering, that particularly in power electronics, the maximum utilization of solar energy and research area is moving in the solar energy field. Why? Because in India, we have given information or assurance to the European countries that by 2030, 40% of our power production will be by non-renewable. We all know that there are many ways of non-renewable energy sources. Okay, so hydro, solar, nuclear, biomass, like that. But in our country, solar energy is very much available in abundant. So tapping of solar energy is very easier for us, whereas tapping of any other non-renewable energy sources, any other renewable energy sources. Okay, so this solar energy concentration is more on the solar energy. So for tapping this solar energy, we use photovoltaic cell. So what is this photovoltaic? So solar photovoltaic, what is this? So the photovoltaic is the name which is obtained from the Greek words, that is photo means light and voltaic means voltage. So the voltage obtained from the light, we call it as photovoltaic. The advantage of this is we have very much abundant of solar energy. Disadvantages, we utilize AC alternating nature, but whereas the output of solar is DC, so that we have to be converting. And another major disadvantage is solar is available in the daytime and not available in the night time, whereas even in daytime it is varying in nature. So as a result, this forms a major disadvantage in using the solar energy, but that disadvantages are overcome. So we can use in the daytime, and how effectively we are going to use it in the daytime. So that's we are going to see it. So the solar energy is made or utilized by using the photovoltaic cell. This photovoltaic cell is made of silicon, so where photons and electrons concept are used. So in our physics, we have studied that the loosely bound valence electrons will be there. So these valence electrons are much available in our silicon. So these valence electrons are tapped by the force applied by the photons, and all these are collected in one end, and thus a current is made to flow. So here, in using solar energy, two factors comes in here. So one is irradiance and another one is temperature. So two parameters, voltage and current, are always, we are speaking in electrical energy. So that these two parameters are related to these two factors of the solar energy, that is irradiance and temperature. So temperature is the current situation or current hotness. Irradiance is the radiance, how much falls on a per square meter of area. This irradiance is related to the current. Higher the irradiance, higher the current. Lower the irradiance, lower the current. Similarly, temperature is related to the voltage. Higher the temperature, higher the voltage. Lower the temperature, lower the voltage. So since we have irradiance and temperature varying throughout the day, we are call it as variable output. So the solar energy output is variable output in nature. So to obtain constant output nearly most of the time, we use the maximum power point tracking system. So which we'll be seeing in later task. So before that, I'm going to show you the modeling of the solar system in MATLAB. So basically, for which a detailed derivation is given by this person, okay, by this reference. So using this reference, I'm using the equations only here. The of the equations can be detailedly seen in this reference paper. So a sample diagram is considered here. So this is a ideal PV cell. This ideal PV cell shows a current source, which is a current produced in the PV. Since a silicon is used, a diode concept is introduced here. So the diode concept, will be there. So a diode loss will be taking place because of the current flowing through this diode. So a overall current I flows out of the PV cell. So this is the normal. So now I apply my KCL concept at point A. So by applying my KCL concept at point A, I get my equation I equal to I PV cell minus ID. So this is my basic expression. So the diode characteristics equation is given based on that ID is defined here. So when I substitute this equation 2, which is the expression of ID in equation 1, I will be getting the equation 3. So the parameters, what is QV and all is given here. So I is my current output from the panel. IPV is the current generated by the incident light, and I0 cell is the leakage current of the diode. ID is the Shockley's diode equation for current through the diode. Q is the electron charge, which is a standard value. V is the voltage across panel, which produces because of this current I flowing. A is the diode ideality constant, K is Boltzmann constant, and T is the temperature of PN junction in Kelvin. So here inside the simulation, the temperature value is in Kelvin. So this is the ideal PV characteristics, and for example, I am taking here, this is in y-axis we take the current, and in the x-axis we take the voltage, and this is the V maximum, and this is the I maximum point. Okay, IMP indicates I maximum point, V maximum point. In both this point, in I maximum point, voltage is 0, and V maximum point, current is 0. So in both these points, my power is 0 because P equal to VI in DC. So any one parameter is 0. In both these points, my power becomes 0. So if you see here, current is maximum and voltage is 0 means this is short circuit condition. And voltage is maximum and current is 0 means this is open circuit condition. So this is the basic condition in open circuit and short circuit condition of any electrical system. But in practical, it is very difficult to get a curve like that exactly. So a curve we'll be getting a curve like this. So this curve, this point we know it is a short circuit current, and this point we know it is the open circuit voltage. But where I'll get the maximum? So in both these 2 points, short circuit current point and open circuit voltage point, my power is 0. But for utilizing the solar cell, I want to get the maximum output. So maximum output is around this point. So this maximum power point is applied, and the voltage at this point we call it as roughly at this point. This is my voltage maximum point, and my current is approximately here. This is current maximum point. This is around 80 to 90% of the maximum value. So this power should be maximum so that the panel is maximum utilized. So for that, they say a factor called fill factor. In short, they represent as FF. This FF is use this factor so that the power P equal to FF into voltage open circuit and current short circuit. This fill factor is always less than 1, and if it is very close to 1, that particular solar panel is the best solar panel. Initially, in the starting period or newly purchased solar panel, this factor will be around 0.9. Okay, as aging factor comes into the role, so this factor goes on decreases, and the factor goes on decreases, as a result of which the FF reduces. Once the factor decreases very much, less than 0.5, the solar panel has to be replaced. So the ideal PV cell is the what we have seen now, but in practical there will be further some more drop. So as I said, so my current I is not the same current I here. So this current at this point, it is now I'm introducing another term IM. IM is the current outside of the ideal PV cell, and we have 2 parameters, RS and RP. This RS indicates the drop in the current value, and this RP indicates the drop in the voltage value. So the actual current and voltage produced here will not be available here. So that drop is indicated by these 2 parameters. So earlier time we have seen this I equal to IPV minus I naught cell into this term. Now an additional term is added. So this term is the loss taking place in the current and voltage in practical cell. So this expression now, current expression gives now the practical expression or for a practical PV cell. So as I said, this IM equal to IP minus ID without any additional drop. This is the expression which is going to form. The derivation for this is given in the reference paper, and this is there. So using this, I am going to model this expression in the MATLAB. So if I model this expression, the first term is I'm going to see here V, RS, NP and NS and I. So I'm going to frame this expression. So V plus INS RS by NP. So V is added with the second term. RS is divided with NP and then multiplied. So I'll using these 3 terms, I'll be getting RS into NS divided by NP, that is multiplied with I. This I is multiplied. So at this point, I'll be getting I into RS NS by NP. So this is what my earlier expression. So I into RS NS by NP, that is added with my voltage. So this is added. So this point I'll be getting this. And here again, another expression, my earlier expression. Q by NS AKNSST. So Q by by AKNSS is taken and this temperature is taken here. Okay, so these two multiplied and divided will be given here. So this is divided with NS. So this term alone without NS is called as BTA. That's used for our earlier next analysis. So this multiplication division is given here. So these two are multiplied. Now you have to take E power, these two terms. E power is done here. So that point it is subtracted with 1 here. So this whole E power term is subtracted with 1. So that is that here I naught and NP. NP is number of parallel panels. Okay. So I naught by NP is there. So this is given here. So this is taken and multiplied here with this term. And finally IP and NP are multiplied. Okay, this term, and this is subtracted. And this gives my the expression. So in a similar way, my I naught is taken. So this I naught is taken and it is represented like this. So this is mathematically modeled as shown here. So I will be getting this like our earlier case, it is mathematically modeled. And similarly, my IPV is done. IPV equation is given. And this IPV equation is mathematically modeled as shown here. So by combining all these things, we will be getting this expression. So here, these are all the inputs I have to give. NP is number of panels in parallel. NS is number of panels in series. And T is the temperature and irradiance. These are all the factors we should be giving. So this constitute this. So my RS and RP are added here. So this is the two terminals. So now this complete block is given as a subsystem. So temperature and irradiance is given. So this is connected to the load. So the current flowing and the voltage across this is done. So this is how a mathematical model of PV system is done. So in this case, as I said earlier, the temperature and irradiance cannot be varied. So it is an open loop condition. Here the temperature and irradiance are fixed. It cannot be varied. Therefore, to bring in a variation, I have to use the MPPT. So MPPT is maximum power point tracking system. So maximum power point tracking system is a closed loop mechanism. So this closed loop mechanism, to implement MPPT, I require a DC-DC converter. For implementing the closed loop mechanism, I require a DC-DC converter. So without DC-DC converter, this tracking cannot be done. So what is this MPPT performs? So we would have all learned in circuit theory maximum power transfer theorem. That is, my load resistance should be equal to my Thevenin's equivalent resistance of the circuit, or load impedance should be equal to the Thevenin's equivalent impedance of the circuit. So what we have to do, we have to continuously adjust the impedance of the load side, so such that from the solar array point of view, the PV system operates at maximum power point. So how to vary this impedance? So Z equal to V by I. Okay, voltage by current. The impedance is varied by changing the duty cycle. So if I change the duty cycle, what happens? My output voltage changes. So default, my current will also change. So my impedance will also change. So by continuously varying the duty cycle in the closed loop mechanism, I can bring to a point where the maximum power can be transferred from the solar, or in other words, maximum voltage and maximum current obtained from the solar cell. So for this purpose, we are using MPPT algorithm, which is a closed loop control mechanism. There are very much various traditional methods of MPPT techniques: perturb and observe method, incremental conductance method, parasitic capacitance method, constant voltage method, constant current method. In this dominantly used or perturb and observe method, we call it as P and O, incremental conductance method. In short, we call it as IC method. In perturb and observe method, we use voltage and power of the current and previous states. Based on this comparison, the duty cycle is varied. Whereas in incremental conductance method, the voltage and current are used, and based on the previous and current mechanism, these are used. So this closed loop mechanism, perturb and observe and incremental conductance are traditional methods. To overcome this, soft computing technique methods are also used. So for example, fuzzy is used dominantly, but PSO, particle form optimization, are used for this MPPT algorithms. So as I said, this MPPT algorithm to implement, we require a DC-DC converter. Without DC-DC converter, MPPT algorithm cannot be implemented. So what is a DC-DC converter? A DC-DC converter, we call it as a DC transformer, which transforms voltage from one level to another level. So that is the case here. So as the voltage changes, default the current is going to change. For example, I'm going to step up the voltage, then automatically current is going to step down. In general, the basic expression in any transformer, that is V1 I1 equal to V2 I2, is very much applicable for the DC-DC converter also. So we have seen a closed loop control using MPPT algorithm. Whereas in DC-DC converter, there are another category of closed loop control. So that is based on my load requirements. So my load requirements has to be satisfied. That is, from my load side, the voltage and current has to be maintained. So for that purpose, we are using some traditional and non-traditional methods. So some of the traditional methods are voltage mode control. Sorry, it's current, not control mode control. It's current mode control, PID mode control, sliding mode control, classical off-cycle pussycat control, hybrid pussycat control, direct mode controls. So here dominantly used are voltage mode control and PID control. So the non-traditional methods are fuzzy control, neural networks, stochastic algorithms like PSO, cuckoo search, etc. So in the closed loop control, any converter, it can be either it can be a DC-DC converter or inverter, whatever be the converter. The input is taken, so the output is there. So the output is compared with the reference voltage, and this reference voltage is given to the pulse generator, that is the repeating sequence, and based on the pulse generator, the output pulses is produced, and that is the duty cycle or duty cycle signals are produced, and that is given to the converter. So this closed loop mechanism is formed. In open loop control, the drawback is we don't have any control over the outside parameters or the required parameters, whereas in closed loop, there is more control. And another advantage of closed loop control is the distortion and noise levels are very much reduced. Voltage mode control is a very standard form. The little bit advanced form is the PID controller. So in PID controller, we have the standard expression. So based on that expression, the values of P, I, and D are selected. That is, the KP, KI, and KD values are selected. P stands for proportional, I stands for integral, and D stands for derivative. So there are two types of closed loop control we have seen in this DC-DC converter. So for utilizing the solar energy, one type of closed loop is for utilizing the solar energy to the maximum. That is, MPPT algorithm is required for this. And another one is we have to control the load set parameters. We require a closed loop control. So these are two different closed loop controls. So it can be used for any converter, DC-DC converter. Here I shown the IK DC-DC converter, which we'll be seeing later. But in current situation, the current closed loop control should be like this. So yeah, one single controller which has to control both my MPPT and closed loop. So this is the research nowadays it's going on. So sample, I have taken a buck converter. You know that buck converter is a step down transformer like operation. So where the output voltage is less than the input voltage. So a simulation is shown here. So the MATLAB simulation is done here. The design is done. So this circuit shows a simulation for an input voltage of 10 volts and output voltage of 5 volts, and the switching frequency is taken here as 50,000 hertz or 50 kilohertz. Based on this value, the current deviation and voltage deviation is assumed as 5%, and using these values, the L and C values are designed. So if I am giving a 10 volts as my input and my output voltage is 5 volts, so since if you see here, the distortion is very high. On average, I'll be getting 4.5 volts. The output varies between 4 to 5 volts. On average, the value will be 4.5. So if you notice that the distortion here is very high. So now we go for a closed loop mechanism. So in this closed loop mechanism, here in this earlier circuit, I use the pulse generator. So here I use 50% pulse value so that I get my value as 5 volts. If I give 10 volts, I am getting a value of 5 volts here. So instead of pulse with my generation, I have been going for a voltage mode control where I give the reference value. This is my V reference. The output value is taken and V reference value is taken, and this is compared, and the output of this, that is the error signal, is given here. That is compared with the repeating sequence, and this value produces the pulses. So this pulses is given to this gate sequence of this MOSFET switch. So now my required voltage of 8 should be obtained here. So if you see here, my input voltage is 10 and my output voltage is 8. So if you see here, normal voltage control, we have this accurate result, and the distortion is very much reduced. But if you see here, there is an overshoot here. So this is a problem. By reducing this overshoot, it is a real technological problem we will face. This overshoot should not be there. Right? So this overshoot should be avoided. That is a real task. But we are now just seeing the simulation part. So next one, I'm going for a PI controller. If I go for PI controller, the P stands for proportional. It is used to reduce the error. So my proportional value will be selected such a way that based on my error. If the error is more, my proportional value will also be more. If that's the case. Integral means, I means integral. This integral indicates that I'm using the past values. D is differential, which indicates that I'm going to use the future values. So in this case, we are not going to use any future values. So ourselves, we are restricting this with P and I. So we call it as PI controller. So in PI controller, this circuit, my input voltage is 100 for a change, and this is for 70 volts, which is my reference. So based on this, error signal is produced. So there, the comparison, okay, we'll give it using a sequence here. So here I give it my PI controller. In this PI controller, there are two values, Kp and Ki. So that two values calculation is very important. So that we'll be seeing later. So that is given to the repeating sequence. So I get my 100 volts. So my output voltage is 70 volts. So as I said earlier, my Ki, Kp values is very important here because see the overshoot. So my required voltage is 70% and my peak overshoot is 120 volts. So nearly a deviation of 50 volts. So proper designing, I have randomly given it my Kp and Ka value as 1. So that's the case here. So proper designing is required. So what is the procedure of proper designing is seen later. So this is another form. So there I used a PID controller and a repeating sequence form. And here instead of that, this is the latest MATLAB versions is available. That is PWM generator. So the duty cycle signal PID output controller output is the duty cycle signal, and that is given to the pulse generator. The pulse generator output is directly given to the MATLAB. So this is the case. So same one, earlier one, I'm giving it as 10 volts, and I'm giving my reference as 5 volts. So I'm getting roughly around 4.377. So this calculating of Kp, Ki is a very important task here. So for that purpose, Ziegler-Nicholas method was the earlier proposed method. In the Ziegler-Nicholas method, so the concept used here was initially the I value and D value are set to 0. And the Kp value is so the maximum gain up to Q, maximum oscillation is taken as period is taken as Tu. So this value Ku and Tu is to be increased and repeated. So in this Ziegler-Nicholas method, and is obtained, the Kp, Ti, Td and Ki, Kd. So next slide. So if I know Ku and Tu from point for using these values, then the peak over. So there are some when the hello, sir, is it audible? Hello.
Sir?
Hello.
Sir, it's audible, sir?
Yeah. Is it audible for you, sir?
Yes, sir. Yes, sir.
Yeah. Okay, then I'll continue.
Okay, sir. You can continue, sir.
So as I said earlier, the fuzzy controller is the one which can be really implemented. So this fuzzy controller can be directly used for signaling using the for generating the pulse width sequence, or it can be indirectly used for the PI controllers. Two types of fuzzy logic controllers are available. So this diagram I shown here is directly used to generate the pulse width modulation signal. There is another way where the fuzzy logic can be used is calculating the Kp, Ki values. So instead of not using Nicholas method, because Nicholas is a time-consuming one and it's a very step-by-step mathematical process. Instead of that, we can use the fuzzy logic controller in finding out the Kp and Ki values. Now future methods are there. As I said earlier, even particle swarm optimization is used, and cuckoo search are used for generating this Kp, Ki values. In this case, the fuzzy logic used here is single input one, and that is the error signal is used, and that error signal used here is used to produce the pulse width sequence. So little bit, I'm going in detail with fuzzy. So what is fuzzy? as the name fuzzy suggests, vagueness. I don't know what is the value here. So what is the duty cycle should be given for getting the required output? So that is not clear for me. So I'm using a fuzzy system. In fuzzy system, there are two processes. Majorly is fuzzification and defuzzification. So the range in real time is completely different. For example, I'm going to consider an example that is automatic fuzzy controller for our air conditioner system. So in this, the process here is the temperature of the room temperature. For example, say I'm in Chennai. So the temperature varies here from, in all the year, it may vary from maximum from 18 to 45 degrees Celsius. So this is the range. So in this range cannot be used by the fuzzy controller because fuzzy has its own limitations. So in fuzzy, there are only two ranges, that is either 0 to 1 or -1 to 1. So these two ranges only can be implemented. So the process in which I am going to convert this fuzzy from this actual range to the range of fuzzy is called as fuzzification, and rectification process from fuzzy range to actual range, how I'm going to rectify it, which we call it as rectification process. Okay, so the defuzzification process. So fuzzification is converting the actual value to fuzzy values. Defuzzification is converting the fuzzy values to the actual values. So this is the diagram fuzzy. So input is given. So this is normalized, and this is fuzzification. So for doing this fuzzification itself, I should know the knowledge about the system. Without knowing the knowledge about the system, I cannot implement this fuzzification process. So yeah, only an expert can develop a fuzzy logic system. Once that expert has done it, developed it, others can use this. So first, an expert is required for developing this. So as I said in AC, I have to know what is my temperature range. If I know that only, I can do this fuzzification. Next, once this fuzzification is done, next is my inference. So for a particular condition, a rule is, hello? Hello? For a particular condition, hello? For a particular condition, I have to use this rule. So, for each system created, so that rule is created here. Based on this rule, output, inference and output uptime, that is my defuzzification process. So once my defuzzification process is done, it is given to the plant. So output is produced, and this block diagram shows two input condition and one output condition. One input is input and another one is change in input. So two values are there. So in defuzzification, various methods, how I'm going to extract my output value, various methods are there. So these various methods, of which the centroid method is the most successful one. So some of the advantages of fuzzy system: power system control, fault detection control, adaptive ones, missile control, aircraft, steam engines, traffic light controls, which are using in real time, is of fuzzy control only. So little bit detailed one fuzzy. If I type fuzzy, I'll be getting a system like this. So in this system, so first I have to define how many variables. So add variables, input side, I will make it as 2. So first one is my first input. So here, this is the range I have to give. So for example, here I have taken 15 to 35. So this one we call it as membership function. So M of 1, membership function 1, membership function 2, membership function 3. So in this range is given. So this membership function starts from 15 and has a peak at 20 and have the lower part 25. Similarly, M of 2 will have value as 25 and 30, and M of 3 will have value from 25, 30 to 35. Similarly, this change in error, the temperature change can be maximum of 5 degrees. Either in the 5 degrees is also not possible. The maximum we are taking as 5 degrees. So maximum it may be from 1 or 2 degrees to change that. So that is what. So here also 3 condition is taken here. So output is we are taking here 5 conditions. So what is going if these 2 conditions, what is going to be my output? So here I have to give. So for 2 inputs, so I have to give. If input is in this case, first one input is M of 1 and input is M of second input is M of 1. My output is M of y. That is, so in this case, my temperature is low. Change in temperature is also negative. That is getting decreased. Next, my output should be in the outside. So I have to maintain room temperature. I will be having higher side. Second, M of 1, M of 2 will be of different. So in this case, M of a temperature is low. Here, M of second one, M that is in the positive side. The temperature is rising. So what I should do my AC, the temperature has to be reduced. So this is a simple fuzzy logic simulator for temperature. Rules are given. So any implementing fuzzy logic, our first step is to check it. So this is called as rule viewer. So in this, we have to give both the inputs and see that output. So once this output is perfectly right only, we can implement the exception. You are not getting output in viewer, then it is waste of time implementing in fuzzy controller. So I'm going for a boost converter. So in this boost converter, the sample circuit is given. So here the input voltage is 5 volts and my output voltage is 10 volts. The closed loop mechanism is shown here as there is given as reference. So my input voltage is 5 volts, output current and output voltage 12 volts. As usual, the distortion is reduced here. And this one is the another fuzzy model, which another solar model, which is now available in the latest version of MATLAB, is 2019. This PV array is used. So in this PV array is default mathematically programmed. So 2 parameters we give it is sufficient. That is irradiance of 1000 and temperature is 50. We give this, a solar output will be there, will be available. So in this MPPT, I am going to use a fuzzy logic controller. So a fuzzy logic controller, I am going to use 2 inputs, that is my voltage and current. Okay, this voltage of PV and voltage of current is there. So I have used a memory. Why is memory? Means it uses the previous state value. So a error signal of voltage and power is current is produced here. So power is calculated here. So this is implementation of perturb and observe method. So change in voltage and change in power is taken and that is given to input as fuzzy. So this is of this the duty cycle that is given to the pulse generation. So the duty cycle can be recorded here and the pulse signal is produced here. So this controller is what fuzzy.fizz. The fuzzy.fizz is the MPPT.fizz. MPPT.fizz is the model should be created as shown in the earlier one. So this is the MPPT one which we have created here. So this one is my voltage and this one is my power. These two are given as a input to this MPPT and output is taken. So this is the sample one I have created here, MPPT controller. This is the input one as change in voltage, change in current, and this is my output. One more addition of this is the plot can be plotted here. So the current variation plot can be. So in the technical PV array, this plot is there. if this plot is given, then a curve. So the first one shows my current and voltage, second one shows my power and voltage. So in this, the maximum power is obtained in roughly around 26.6 volts, and maximum current obtained in that. First we have to note this, when around 26 the maximum voltage, maximum power is obtained at this voltage, and at 26 what is the maximum current? It is around 4.6 or 4.7. So when I run this MPPT in fuzzy logic MPPT, so I get around 26 is my voltage and the current is around 4.43, and this is the maximum power my MPPT can produce. So this control, MPPT control, is done by fuzzy logic. So that is the duty cycle is produced and pulse is given to this MOSFET. So this is the boost converter. So and I get my voltage. So these are all the conventional buck converter, boost converter, or the conventional current. But what happens when why we require to go for high gain DC-DC converter? So the high gain DC-DC converter is used because there are a lot of problems in using this DC-DC converter conventional type, because the gain is less here, and next one is the problem used here is stepping up value is, so the gain is less, the stepping up value is also less, so it cannot be used for our real-time applications. Using of transformers are becoming very bulky. So nowadays the advancement in this field of power electronics has made a concept called high gain DC-DC converter. So this is the classification of DC-DC converters. So DC-DC converters are two types: low gain and high gain DC-DC converters. In low gain is further classified into two types: low gain low power converters, low gain high power converters. High gain also, high gain low power converters, high gain high power converters. So our concentration is this high gain high power converters, because we require high gain and high power for our domestic usage. These are all used for smaller applications, but for our domestic usage, we have to go for this. I go for this voltage lift converters. So this category we call it as lower converters. Lower converters is the recent advancement in the field of high gain, high power converters. So the advantage of using high gain, high power converters is, if high gain converters are used for photovoltaic, we can replace the usage of transformers. So the transformers can be eliminated here. So that is the biggest advantage, or because of using this high gain DC-DC converters. So as a result, the cost and size of the converters for real-time applications can be very much drastically reduced. And another advantage is high gain. At lower duty cycle itself, I will get the required output voltage, as a result of which the voltage stress and all the things are reduced across the switches. So the lifetime of the system is also high. So as I said, the voltage lift techniques can be used here. So the voltage lift technique is a concept in which a diode and capacitor is added to the traditional circuit. So by adding a diode and capacitor, the traditional circuit can be used. So for example, the boost converter which I shown earlier, to that circuit a diode and capacitor is added on the output side, then we can call it as self-lift boost converter. Okay, so like that. So that is called as voltage lift techniques. Here a capacitor and here diode is used. So diode generally is used to avoid the reverse flow of current. So if I use single diode and single capacitor, it is called as self-lift configuration. Whereas if I go for two stage, this lifted voltage is again lifted, or it is re-lifted. We call it as re-lift. Therefore, in re-lift circuit, we will be having two capacitance and two diodes in addition to the existing circuits. If you want stage, 4 stage, all those things, triple or quadruple, they call it as super lift converters. So this is the stage here. So self-lift, re-lift, and super lift converters are used now. So advantage of this converter is, as I said, voltage transfer is very high. So the self-lift is arithmetic progression, super-lift is geometrical progression. So the output voltage level is becoming very high. So for a small example, a normal voltage gain of boost converter, this is the formula relation between output voltage and input voltage. Whereas if I go for relift, it is being doubled. If I go for super lift, it is exponentially increased. So this shows that what is the advantage of using high gain DC-DC converters. So if I introduce high gain in a solar utilization system, then automatically we can replace the transformer. So one example which I take here is a self-lift buck converter. So the normal, this diode and capacitor. This part is the basic my buck converter. To this diode and this capacitor is added, and this is my filtering part. So I select a system of 96 volts, which is very easily stepped up to 320 volts, and switching frequency is 50 kilohertz. So based on these values, these LC values are designed. So in open loop control system, I give this simulation, 96 volts is given, and approximately I'm getting 313 volts. So it is switching what? So the values are switching in between these two. So this is this, the oscillation is there, this has been circling. So now voltage mode control. So this error is reduced, so I'm getting around 320. My reference value is 320. Why I'm giving here minus 320? Because in buck converter the output voltage is also getting due here. The output controller. So PI control is there. So I am in this case I am giving KP and KI directly. So KP and KI is given directly. So that is given to the sequence. So that value is done here. So I get the output voltage like this. And last one, I use a fuzzy control here. So in this fuzzy control, so value is given is single input. So single input fuzzy controller is given here. The error signal is given here, and the value is defined. So I'm getting a constant output here. And last only, just I want to implement this perturb and observe algorithm in closed loop control. So the flow chart is, so as I said, power and voltage is used here. So first we have to measure voltage and current from the panel. Power is calculated multiplying these two values. So previous values is there. So we have to find the change in values. So the change in values, del P and del V is calculated. If del P is 0, there is no change. Therefore, no change in the duty cycle. Same duty cycle can be given. No, there is a change in power. So now I'm checking whether the change in value is positive or negative. If change in is positive, we check it for change in voltage now. Change in voltage is also positive, then duty cycle is reduced. Whereas if change in voltage is negative, the duty cycle is increased. The similar way for change in power in negative, if the change in power is negative and I'm checking change in voltage is negative. If change in voltage is negative, both are negative, then we are going for added duty cycle, or otherwise we are decreasing the duty cycle. So this is the case here. So a solar system is implemented here. So this part I am not taking it as open loop part. So this condition is given here. This is the MPPT here. So the voltage and current are measured, and voltage and current values are taken here, and this is delay part is introduced. So this delay part is introduced, and voltage and current are multiplied to get the power here. So power delay is introduced, and on two values it is combined and given here as a error signal, and it is obtained is given as the gate pulse to the switch. So for this MPPT which we have developed, we get a IV curve and PV curve. So the voltage obtained here is roughly around 110 to 120 volts. So there the maximum current will be obtained. So that is the obtained here. So similarly for this, the output is obtained. My required output is 320. So if this 320 I'll give it to the inverter, I can get the required voltage for my low output load. Similarly, my algorithm, as I said earlier, here voltage and current is used. So voltage and current is there. Previous state values are also stored. So change in voltage and change in current is there. So the change in voltage is 0. Next you check the change in current. The change in voltage is if change in current. If change in voltage is not equal to 0, next I find out the ratio of whether my change in current by voltage is this. So based on this condition, I check it and vary my duty cycle. So here I use simulation. I use my mathematics. Those values are recorded and checked here. So programming function is introduced here. So and the values are taken as input here. So these values are taken and given, and based on this, the signal is produced and run. So similarly, I obtain here. This is the PV curve and IV curve of the IC algorithm, and my output voltage and current is obtained like this. So MPPT algorithm is shown here using IC algorithm. This one using P&O algorithm. These two concepts just using the implementing fuzzy controller. So fuzzy controller. So before going to the fuzzy controller, this is the output I have got, which is very close to my those values. So fuzzy controller, two values I have taken. So my voltage value is in volts. So my range I am taking for change in voltage value as plus to minus 2 volts. So this 5 volts range I have taken. So it is a very high value only. So maximum I can take. So power I am taking power is a product of 1.5 for example. So I am very taking drastic. My cycle only duty cycle it will be 0 to 1 only maximum. So that is this is the I have taken. So electric labels I have given here as negative medium, negative small, 0, positive small, positive medium. So based on that, these rules are created. If both are negative, the output is 0. So if negative and this one is output positive medium, so like that condition is taken. So based on the values I have taken from Bartow and incremental and achievement, this is our frame. So for as I said earlier, I have to check in this. So I have checked what is my change in voltage and change over here, and whether this cycle uptake is right or is closely. So I am getting an accurate result here. So I am getting around voltage there. So the first control and the results of them. So I conclude here. So what I conclude here is, so this presentation gives presentation gives you a detailed analysis of the electronic converters can be used real time. So queries please. Sir, is it audible?
Thank you, sir. Participants are requested to ask any queries to our special speaker. Please, sir. Participants. Any queries?
Hello.
Yes, sir. Ask from our guest.
This is Muthu speaking from Chennai. Sir,
Tell me.
the converter is there. Two types of converters. Is there
Yes, sir.
AC to DC and DC to DC? Two types of converters are there.
Yes, sir.
Then which type is more efficient in the solar system?
Sir, two types of converter. We can't speak about solar systems, sir, because both converters are required. As you said, DC-DC converter is for setting up the DC voltage, whereas for DC to AC converter is for our purpose, because all our loads are AC in nature.
Okay.
We can't compare these two things. For utilizing solar energy, we require a DC-DC converter. Without DC-DC converter, solar converters cannot be used.
Oh, solar energy is utilizing for the home application also.
Yes, we are utilizing it, sir. There are many applications. We have solar rooftops. We have solar car sheds, solar parking areas.
The solar cell used in the automobiles, roof.
Yes, sir. Solar vehicles. Yes, sir.
Then, for suppose is a running condition, the efficiencies are same or in any reducing?
It will surely be reducing, sir. Our solar efficiency, that is also one of the drawback. The efficiency is around 40% maximum.
Okay, sir. So during running time, it's slightly reduced.
Yeah, it surely will reduce.
Okay.
Based on our load condition,
Okay. Okay.
it will be decreasing. So for that purpose, only to maximize the utilization, we are using the MPPT algorithm, sir.
Okay. Thank you, sir.
Any other
Okay,
participants?
thank you. Welcome, sir.
Any other participants have queries? Please.
Sir, I have one question.
Yeah,
Yes,
tell
ma'am.
me, sir.
Sir, I am Tanuj from Bareilly. Hello, am I audible?
Yeah.
Sir, I just want to ask one thing. This DC to DC converter that we are using, which type of power electronic specific component we have to use here? I want to ask. Whether chopper, whether SCR, which type of power electronic converter we can use?
Sir, I'm not clear. Please repeat me.
Sir, in this DC to DC converter that we are using here, one question is that is it similar to, MPPT and DC to DC converter? Is it one and the same thing or both are different?
No, sorry. I'm not able to hear you.
Sir, Guruji, sir, we can't able to audio. Hear your voice, sir. Please audible, sir.
Sir, I want to ask this DC to DC converter that you are using now, DC to DC converter.
Yeah, we are using DC to DC converter. Yeah, tell me.
So is this DC to DC converter and maximum power point trigger, are they both one and the same thing or they are different?
They are different, sir. For implementing MPPT algorithm, we require DC-DC converter. Without MPPT algorithm, DC-DC converter can be functioning separately also. I have shown my simulation. No, in open loop condition of any DC-DC converter, there is no MPPT algorithm at all.
No, I have actually connected one solar PV module to supply load in my house, 2.5 kilowatt. So there I have just purchased one controller which is called charge controller. So I'm just asking you,
sir,
that
inside the charge controller, a DC-DC converter will be surely there, sir.
Yeah, that is what I am asking. Is that charge controller a DC to DC converter only?
Sir, inside the charge controller, your MPPT controller is implemented using a DC-DC converter.
Okay, means DC to DC converter is inside that charge controller.
Yeah. DC-DC converter is a small switch, sir. It is a very much small part. It will be there in the PCB.
Okay, one question more. This solar PV cell, will this come in the category of voltage source or current source?
Sir, actually we will be using it. Sir, it's in turn both are combined. A module solar cell we take it is a current source, but we are for your utilizing purpose we require both voltage and current. No, both
So
are
it will be
interrelated.
it will be called as a dual source, no? Both voltage and current.
Not we can't say the dual source that whenever a current flows across a resistor, your potential difference will be there, no? That potential difference is what we are utilizing. A current flows in a closed circuit.
This solar module, will it be called as a voltage source or a current source or both? That is my
current source. Current source.
Yeah. Okay. Thank you, sir. Thank you.
Thank you.
Thank you, sir. Any other participants or have a queries, please? Any other have a queries? Any participants? Sudha, yes, tell me, ma'am.
Sir, here we using solar system only, but many other renewable sources available in the environment. So
very much are available. Yeah.
If you consider instead of solar energy using wind energy, it's possible or not, sir?
Wind energy is completely a different topic, ma'am, because wind energy, the output is AC in nature.
Okay.
We'll be using wind energy output in electrical form.
Okay.
The nature is in all thing in nature, so it is completely different track of study where you use transformers and all those things.
Okay, sir. Only we using the solar energy.
Yeah, here we have. I have restricted myself to solar energy application. As I said, in recent times we have many topics.
Okay, sir.
Okay, myself I have represented of field of power electronics, or how I can use soft computing techniques. That too particularly fuzzy logic. How fuzzy logic can be used in our power electronics converter.
Okay, sir. Okay, sir.
Okay.
Thank you, ma'am. Any other participants have a queries? Sudha, sir, shall we close, sir?
Yes, sir. Yes, sir. You can wind it off, sir.
Okay, sir. If any participants have some other queries, you may contact our speaker through WhatsApp or any other through mail also. So, on behalf of our institution and our department, I would like to